This review is about dynamics, and let's see how we can work with this system of objects. Now, the first question, most of the students did all right. Basically, we have a mass 1 and a mass 2 on a pulley, and we need to find something about the acceleration later, but in order to do all of this, we need to work with the free body diagram. So somewhere here is the mass 2 and somewhere there is the mass 1. In both cases there is a force of gravity. In both cases there is a force of gravity, but he tells us somewhere that mass 2 is greater than mass 1. So the force of gravity on mass 1 needs to be a small arrow. The force of gravity on mass 2 has to be a great arrow. And if we want, we can say this is force of gravity 2 and this is force of gravity 1. And there is the force of tension, but the two tensions are on the two sides of the same rope. So the two tensions have to be equal in length. And also we have to be a little bit careful, since the object 1 is moving the object 1 is moving upward, we need to make the tension a little bit greater than force of gravity 1. And since the object 2 is moving downwards, we need to actually make the gravity a little bit greater than the tension 1. So a good free body diagram should approximately look like this. And if we also want, we'll make tension and tension that have equal length. There is no normal force. There is no friction, there is no applied force. These are the only forces that are applied on the system. We continue with finding the acceleration of the system. Now, it helps us if we draw the same free body diagram on the diagram that it is given. So we have the force of gravity 2, which is m2 times g, the tension that it is upward, the tension that it is upward, and the force of gravity 1 that it is m1 multiplied by g. And because we have two connected objects, we will not work on object 1, we will not work on object 2, but we will work for the system. So we mention that we are working for the system, and since we need to find acceleration, we will apply F net. It is equal mass, but when we say mass, we mean mass of the system. So total mass multiplied by the acceleration. Now, when we say F net, we care only about external forces. And external forces are only the force of gravity. The tension is a force from within the system. So we don't care about the tension, we're going to do force of gravity 2 minus force of gravity 1. The reason why we're doing force of gravity 2 minus force of gravity 1 is because there is a great force that pulls the system in the counterclockwise direction, and there is a smaller force that pulls the system in the clockwise direction. So we do m2 multiplied by g minus m1 multiplied by g is equal, when we say m total, we mean m1 plus m2 multiplied by the acceleration. And on the left side, if we want, we can bring the g as a common factor. So we'll have m2 minus m1 multiplied by g is equal m1 plus m2a. And in order to leave the acceleration alone, we're dividing over m1 plus m2. Actually, I think that the m should be capital. Yes. So capital M1 plus capital M2. And this is our final answer, M2 minus M1 multiplied by G divided by M1 plus M2. We can continue to the next part, which is he's mentioning now that, okay, we make an experiment and we bring these masses. So we place a mass 1 that it is 1 kg, then we replace it with a mass that it is 2 kgs, and so on. We do the same thing for the mass 2. We replace the object with something heavier and something heavier and something heavier, and we find different values for the acceleration. And he wants us to indicate which quantities should be graphed in order to find in order to have a graph that the slope will be used in order to find the force, the value of the acceleration of gravity. Well, the answer is we don't know, but we have a look at what we have on the previous question. And on the previous question, we have something that connects the acceleration of our experiment with the masses that we used and the gravity. So we write down our previous conclusion that m2 minus m1 divided by m1 plus m2 multiplied by the g is equal to the acceleration. And again, we need to use this in order to create a graph that the slope will be equal to the acceleration. But we know that the slope is rise over run. So we need the slope, something over something, to be equal to g. So basically, first we will leave the g alone. So we'll say that the g is equal acceleration multiplied by m1 plus m2 divided by m2 minus m1. And we need to make a graph that will show the acceleration. So basically, that will show the acceleration of gravity. So basically, we can say that one kind of graph that we can use is that the slope will be rise over run. So maybe the rise will be this, and the run will be that. This is okay. So we can say that, for example, on the vertical axis, we can write a times m1 plus m2, and on the horizontal axis, we can write m2 minus m1. But it is a little bit better to say that, okay, on the vertical axis, I will have the acceleration, since we already have the acceleration. And on the horizontal axis, we'll have the reverse of what is here. So basically, we'll have acceleration over the reverse of what is already there, which is m2 minus m1 over m1 plus m2. So we can say that on the horizontal axis, we'll have the quantity m2 minus m1 divided by m1 plus m2. Again, both options are correct, but since we already have calculated the acceleration alone, maybe it is better to use one of the two axes as the acceleration alone. And then we need to plot this graph. So we will need to draw the x-axis and the y-axis. On the y-axis, we said that we will use only the acceleration. So we say that the acceleration is measured in meters per second squared. And on the horizontal axis, we'll use the value m2 minus m1, m1 plus m2. Again, any of these two could work. I prefer to work with the second one. M2 minus m1 divided by m1 plus m2. And this is measured in kgs. Now, for the acceleration, we see that the values are 4, 1, 1.1. So we get values between 1 and 4. So I'm going to say that the whole line of the graph will get values from 1, 2, 3, 4, 5. I'm trying to use almost all the space that it is given to me. Now, for the m2 minus m1 over m1 plus m2, we don't have this value, but we can spend a few minutes to calculate it. So we say m2 minus m1 divided by m1 plus m2. So for each single case, we can use calculator and say m2 minus m1 is 1 divided by m1 plus m2, 1 plus 2, so the result is 1 over 3 or 0.33. In a similar way, 1 over 5 or 0.2. On a similar way, 12 minus 5, it is 7 over 17. We need calculator for this. So the result is 0.41. Then we get 8 minus 6, 2 over 14. And again, we need calculator for this. The result is approximately 0.14. And 4 over 24. And the result, let me just check, 4 over 24. The result is 1 over 166 or 1 over, 0.17 approximately. So we get values from 0.14 to 0.41. So my diagram should be, okay, 0, let's say somewhere here it's the 0.1, and we get 0.4 as a maximum value, so maybe it should be a little bit less. 0.1, 0.2, 0.3, and 0.4. Again, I'm trying to use almost all of the space that it is provided to me. And for the first point, we have that the m is 0.33 and the acceleration is 3, so the first point is somewhere here. Then 0.2 and 1.8, so the second point is somewhere here. Then 0.41 and 4.2, so approximately somewhere there. And then 0.14 and 1.15. So the first point, that point is somewhere there approximately, and 0.17 and 1.7. So another point somewhere there, unless I made a mistake in the previous point, 0.14 and 1.15, and it's actually a little bit lower. Somewhere approximately there. So we can see that these 5 points belong on a straight line, and we're gonna draw a line that passes between these points. Again, I understand that finding this was a little bit difficult, but again, it comes from the previous acceleration. Basically, we need the g to be something over something. Any something over something can work. I prefer to work with acceleration on the top and the combination of masses at the denominator. But any something over something can give you the value of this g. So we draw a line that passes through these points, and we need to continue by finding the value of g. Well, we already said that the g is what we have over there, acceleration over the combination of masses, m2 minus m1 over m1 plus m2. However, since we are using the graph, maybe we can say acceleration is rise over run, or delta y over delta x. And if we go to the plotted graph, we will select any point on the straight line. For example, I'm going to select, let's say, this point, and we find that the value is approximately, let's say, 4.1. So 4.1 minus, I'm going to select another point on the same straight line. I'm going to select, for example, it can be random, okay, it doesn't really matter. I'm going to select this point, or something that has a little bit more suitable values. I'm going to select this point and that point. So 4.1 was the initial point minus 3 divided by the delta x, which is 0.4 minus, well, it is a little bit less than 0.3, so I'm going to say 0.295. And if we go to the calculator, so 1.1 divided by 0.105, we're going to find a little bit more than 10. I find 10.48. Anyway, again, you can take any points that belong on this graph, and when you have a plotted graph with the blocks, it will be more precise, so maybe you will find something closer to 9.8, but anyway, even this value is acceptable. So with the experiment, we find approximately 10.5, and since this is the acceleration of gravity, the unit is meter per second squared. And we continue to the next part, where if we read, he tells us that we change the way that the experiment is conducted. Instead of a pulley and two objects that are hanging, we are placing one box on the table and the other box is hanging. And we need to figure out what is happening to the magnitude of the tension. What is happening on the tension? If the tension on the string is going to be higher or lower. Now, I don't know the answer, but we found before that the tension, I think at least we found before, I'm not sure. Actually, we didn't find the tension before, we just found the acceleration. Okay, I'm not sure about this, but we can use the acceleration to find the tension before and maybe find the tension later, but this will take some time, and time is precious. But we can think a little bit more. In the previous question, in the previous part of the question, we had, wait a minute, we had two forces that were pulling the string. We had the force of gravity on one side and the force of gravity on the other side. So we had two forces pulling the string. This stretched the rope a lot, and this means that the tension was relatively high. Now there is only one force that it is pulling the string, so this means that the tension most likely will be lower. So with common sense, we can say that now there is only the force of gravity on the second object pushing the string or pulling the rope, with a contrast to what was happening before. Before there were two forces of gravity, so there were Fg1 and Fg2 pulling the rope. So tension decreases. Now this is with common sense, and this is acceptable. My guess is that there are other explanations that could be acceptable. For example, because the block of mass 1 is on the table, the net force on the system increases. Actually, what we can say now is that before, the net force was Fg2 minus Fg1. Now the net force is just Fg2, so the net force increases. So since we have more net force, there is more acceleration, and since there is more acceleration, the tension has to be lower. Or if we're not sure about this, we can do the calculations. We can say that in this case, okay, there is an mg2, mass times gravity for the second object. So the F net right now, it is equal mass times acceleration. So m2 times g, it is equal m1 plus m2 multiplied by the acceleration. So the acceleration is m2 times g divided by m1 plus m2. And this is slightly different than what we had before. So now that we have the acceleration, we can find the tension on the rope. We can say that the tension is applied here or the tension is applied there. I prefer to work for the mass one. So we can say F net for mass one is mass times acceleration. So the tension is equal m1 multiplied by m2 multiplied by g divided by m1 plus m2. This is the tension right now. Now, finding the tension for the previous case, it's a little bit more complicated, but we can try to do that. So we can work for the object that moves up. So I will work for mass 1 again. So the F net, it is equal mass 1 multiplied by the acceleration. So tension minus m1 times g, it is equal mass times acceleration. So it is mass 1 and the acceleration we had found it, m2 minus m1 multiplied by g divided by m1 plus m2. So this means that the tension is equal this fraction m1, m2 minus m1, g over m1 plus m2 plus m1 times g. So we need to compare this value with that value that we get for the second tension, and I guess that eventually we'll end up that the first tension was greater than the second tension. And finally, all of these explanations can be correct. And finally, the value for the acceleration of gravity in the second experiment is lower than the first experiment for some reason. And we need to say what could be one reason that this is happening. Well, there are a few things that we can say. Basically, we need to figure out what can cause an error to our experiment. And what can cause an error to an experiment is that maybe we didn't measure the masses properly, accurately. But this is a little bit unlikely. One thing that can cause an error to our experimental values is the motion of this object. Basically, this object is on the table. Okay, he's mentioning that the table is smooth, but no matter how smooth it is, there must be a little bit of friction. So one thing that we can mention is that in reality, in the second experiment, the friction between the table and the mass causes this error. Basically causes our values for the acceleration or the value for the acceleration of gravity not to be completely accurate. Now, if you have any questions, please go ahead.